Hello and welcome to our YouTube channel JK Academy India. In this video, we will discuss about the losses in the transformer, efficiency, and the condition for the maximum efficiency of the transformer. Losses in a transformer. Mainly, there are two types of losses in the transformer. One is core loss, another is copper loss. When AC supply is given to primary winding, a transformer alternating flux is set up in the core. Therefore, hysteresis and eddy current losses occur in the magnetic core. Now, hysteresis loss is when the magnetic material is subjected to reversal of magnetic flux. It causes a continuous reversal of molecular magnets inside the core. This effect consumes more electric power, which is further dissipated in the form of heat or loss. This loss is known as the hysteresis loss, and the equation is PH KH VF BM power 2.6. This loss can be minimized using silicon steel material for the construction of core. Second is the eddy current loss. Since flux in the core of a transformer is alternating, it links with the magnetic material of the core itself also. This induces an EMF in the core and circulates eddy currents. Power is required to minimize these eddy currents. This power is dissipated in the form of heat and known as the eddy current loss, and its formula is PE equals to KE V F square T square BM square. This loss can be minimized by making the core of thin laminations. It is already seen in last video that the flux setup in the core of the transformer remains constant from no load to full load. Hence, iron loss is independent of the load and is known as the constant losses. Second loss is the copper loss. Copper loss occur in both primary and secondary winding due to their ohmic resistance. If I1 and I2 are the primary and secondary currents and R1 R2 are the primary and secondary resistances respectively, then total copper loss of a transformer can be given as I1 square R1 plus I2 square R2, and it will become I1 square R equivalent referred to primary, I square I2 square R referred to secondary equivalent resistance. The currents in the primary and secondary winding vary according to the load. Therefore, copper losses vary according to the load are known as the variable loss. Now, there is one more term in case of transformer known as magnetostriction and its ill effects. The property of ferromagnetic materials due to which their dimensions are changed due to change in magnetic field is called magnetostriction effect. In fact, the applied magnetic field changes the magnetostrictive strain until machine is reaching in its saturation value lambda. This causes change in dimensions of ferromagnetic material. The effect was first identified in 1842 by James Joule while observing a sample of iron. In simple terms, as per this phenomena, if a piece of magnetic sheet steel is magnetized, it will extend itself. When when the magnetization is taken away, it goes back to its original condition. A transformer is magnetically excited by an alternating voltage and current so that it becomes extended and contracted twice during full cycle of magnetization. Hence, when the core becomes magnetized, it expands, then it contracts and expands again as the field is reversed. A 50 Hz transformer therefore expands and extracts at 100 Hz, producing a buzzing sound at that frequency. Transformer buzzing noise or humming noise is caused by a phenomena called magnetostriction. Although these extensions are only small dimensionally, therefore cannot usually be seen by the naked eye. They are, however, sufficient to cause vibration resulting in a noise. This effect also causes losses which produce heat in ferromagnetic cores. Thus, the first cause of humming noise is magnetostriction. The other cause may be due to details of core construction, size and gauge of lamination or joints in the core. The other reasons for humming sound in a transformer may be loosening of laminations, mounting defect, unbalancing or insulation deterioration, etc. Methods to control transformer noise. First one is using low value of flux density core by proper tightening of core by clamps and bolts, by sound insulating the transformer core from tank walls. Now, what is the effect of voltage and frequency variations on iron losses? As we have seen in previous pages that the hysteresis loss is directly proportional to the frequency and the flux density, and eddy current loss is also directly proportional to the frequency square and flux density square. The transformer is operated with the frequency and voltage changing in the same proportion. The flux density will remain unchanged. As obvious from equation, this is the EMF equation of the transformer. Bm equals to E upon this. So Bm is directly proportional to V by F. Apparently, the no load current will also remain unaffected. The transformer can be operated safely at frequency less than the rated one with correspondingly reduced voltage. In this case, iron losses will be reduced, but if the transformer is operated with increased voltage and frequency in the same proportion, the core losses may increase to a large extent which may not be tolerated. Increase in frequency with constant supply voltage will cause reduction in hysteresis loss and leave the eddy current losses unaffected. However, some increase in voltage could therefore be tolerated at higher frequencies, but exactly how much depends on the relative magnitude and hysteresis and eddy current losses and the grade of the iron used in the transformer core. Now, efficiency of a transformer. So for any device, efficiency is nothing but the output power divided by input power. So ultimately this will become output power plus iron losses and copper losses. Output is V2I2 cos phi 2 divided by iron loss plus copper loss. V2 is the secondary terminal voltage, I2 is the full load secondary current, cos phi 2 is the power factor of the load, Pi is the iron loss containing hysteresis and eddy current loss, full load copper loss is the PC I square R equivalent. So the efficiency will be this complete formula of efficiency, and the copper loss vary as the square of the fraction of load. Now condition for the maximum efficiency. So this is the equation for the efficiency, and if the derivative of this will become 0, we will get the result that this should be 0, and therefore ultimately I square R RES equals to iron loss. It means when the copper losses and iron losses of a transformer are same, at that time the efficiency of the transformer will be maximum. Now, effect of power factor on the efficiency. So the efficiency is what we have seen, it is 1 minus losses upon output plus losses. So this will become, this is the output and this is losses. So here we will get 1 minus losses upon V2I2, and this will be the power factor. If we put this losses V2I2 equals to X in the equation, we will get the efficiency 1 minus X upon cos phi plus X. So it will become 1 minus X upon cos phi divided by 1 plus X plus cos phi. The variation of efficiency with power factor at different load for a typical transformer are illustrated in this figure. So this is the load graph and this is the percent efficiency and this is the power factor. So if power factor increases, the efficiency also increases. At unity power factor and approximately 75% of load, 75 percentage of load, we will get the efficiency in between 98 to 99%. But if the power factor is 0.6, the efficiency may reduce. Now this is the graph showing efficiency versus load curve of a transformer. So this is the point A and this is the graph of copper loss and this is the graph of iron loss. Both are intersecting at this point where the percentage loss is 75% and efficiency is maximum. So thanks for watching. We will meet in another video. So take care and goodbye.